All right, hey everybody, this is Nicole, and I'm one of your tutors for ECH 145B this quarter alongside Josh. Today, I'm going to be talking to you about using the Matlab code, analyze packed bed version 3 in order to process your images that were given to you as your data in Google Drive. So essentially what this code does is it takes those images of the column with the silica gel and it interprets the colors of the silicone gel numerically using pixels, and allows you to determine the percent saturation along the length of the column over time. All right. So first, we're going to go ahead and clear our workspace and close all images, and then we're going to also clear our command window. Okay. So this first line that Josh also talked about is allowing you to upload your files and record the path name that you take to get to those files so that Matlab can recall them later. Before we do this, we're going to want to make sure that all of our images are consistent between time steps or between figures, which basically means we want to avoid any column shifts or severe changes in light intensity or blurry images. So before we run this, what we'll do is we'll go over here to our images, and I'm looking at 3 liters per minute cooling trial 2, but you'll have to do this for all trials. Basically, just click on the trials and kind of walk through them iteratively. Make sure that there's no severe blurry images or changes in column position. There are some light intensity changes, but there's not much you can do to avoid that. Just make sure there's nothing super severe, like a complete whiteout. I already walked through all of these images, so just do that as well before you run this code. Make sure that you're being consistent. All right. So when I run this code, it's going to ask me to upload the images that I'm going to be analyzing, and you want to make sure to upload all of the images that are not blurry or don't have column shifts within the same trial. So I'm going to upload all of these and open. All right. And that basically records all the file names and also records the pathway. All right. Next thing MATLAB is going to do in this line is interpret those files as an image. Do not run this unsuppressed. It's going to take a really long time. And depending on your computer's health, it might crash it. So just know that's what it's doing. It's going to interpret it as a sequence or matrix of numbers. All right. This creates a white background for all your figures. And before we talk about this, which is not part of your original code, right, so this is the original code right here. Initially, when you run this and show your image, you'll notice that the image is oriented as it was from your Google Drive. Unfortunately, MATLAB is analyzing your data assuming that your transfer is occurring from left to right, or that your saturation levels are moving from left to right. Whereas here, we're going to be moving from bottom to top, and we don't want that. And so we're going to have to rotate this image to match with what MATLAB's left to right analysis. MATLAB rotates in a counterclockwise direction. So if you want the base of the column on the left side, you're going to rotate a total of 90, 180, 270 degrees. Okay. So in order to rotate, we're going to overwrite that image and do IM rotate. And we're going to rotate the original image by 270 degrees. And then we can rerun this IM show to make sure that's actually what it's doing. And perfect. We got our bottom of the column on the left side. All right. Next step in the process is going to create a cropped image called iCrop0 with dimensions of rect that allows you to only analyze the actual relevant part of the figure, which here is the silica gel. So when we run this, it's going to pop up with the image again, and we're going to select the region that we want to crop out. So we're concerned again with the silica gel. We're going to include as much of it as possible without including the sides of the column or the cotton at the top and bottom. All right. And then once you're done, you're just going to double click here and it's done. And we're going to close this out. When you run IM_show iCrop 0, you're showing the cropped image. And just double check that there's no cotton in the top or bottom and there's no glass. This one looks fine. Next part is using the rectangular region to specify the dimension of interest. Here we're talking about transfer from the left to right, which is actually the width of the cropped image. I know it's the height of the column, but it's the width of the cropped image. And so rect has inputs, or it has outputs of the origins, so X naught and Y naught, the width of the image and the height of the image. So we're going to export image width, and it's going to show up as a number of pixels. All right. The next part here is repeating that, but for all of the other images, not just the first image, using the same rectangular region. That's why it was very important for you to make sure there were no column shifts within the files, because you're going to use the same crop area for each image. And that's specified right here in rect. So we're going to, again, read our files and specify them as I. We're going to crop them using the specified region now. And again, before you can crop them, just make sure that you've rotated. So we're going to IM rotate again, 270 degrees. And that should work. This next part, iBlue, is taking the same cropped image and interpreting it in a blue scale. So instead of using all of the red, green, and blue pigments, Matlab is only going to interpret this in blue. The reason being that the silica gel turns from orange to clear after it becomes saturated. And orange has basically no absorbance of blue, whereas clear has a higher absorbance of blue. And so as saturation increases and we turn towards a clearer color, we're actually increasing the blue pigmentation. And so that's ideal for us because as saturation increases, the blue will increase, and it's a logical way to interpret the data. So this just selects the third indice in the Z direction, which is just the blue pigment. All right. So I'm going to set n is equal to 1 just to show you examples of this code running without running the entire for loop first. So when we run this, we'll get our blue matrix. And then IM_show iCrop is just showing the cropped images. And then IM_show iBlue is showing the cropped images now interpreted only with blue pigments. So if we run this, we'll see the result of that. We see the top being the original image and the second being in the blue scale. So it looks basically black when there's no saturation. When there's more saturation, it turns to more of a white color. It's ideal to work in this kind of grayscale environment for Matlab. Okay. The next thing we're going to do is talk about averaging the cross-sectional intensity in these images. So basically, we're only concerned about transfer from the left to the right, but you'll notice that there are pigments, or there are pixels going through the height of the cropped image as well. And so basically, it's also showing deviations in blue intensity along the width of the column, which we don't really care about. And those deviations aren't due to meaningful transfer. They're just due to maybe discrepancies in packing or discrepancies in saturation level of the beads before you actually loaded them in. So we're going to take a single mean of the iBlue matrix, which basically takes all of the rows or along the width of the column and averages them, so you get a single saturation level for every height in the column. That's all this is doing. And if we run that, we'll indeed see that now we only have a single row that has different values of saturation based on your height or pixel value in the column. The next thing this is going to do is plot those now averaged intensities in red dots alongside your other two images. And so if we run that, we can go ahead and see that intensity starts pretty low at the top of the column, so basically no saturation, and it increases slightly to the bottom of the column. So again, remember that transfer is happening from bottom to top of the column, or in these images from left to right. And so higher intensities mean higher saturation, lower intensities mean lower saturation. It's kind of hard to see in this first image because this is time is equal to 0. So let's go ahead and run this entire for loop and see the actual progression. Right, so you see that as time progresses, the saturation levels are actually increasing the base of the column. The saturation is kind of moving along the length of the column. So saturation is increasing throughout the column. It remains the lowest at the top of the column. Now, something to point out as we watch the rest of these frames progress is that the maximum intensity or the maximum saturation sometimes doesn't occur at the very base of the column, although it should. And the reason for that is that there are issues with there could be issues with the camera, issues with light intensity, again, deviations between different silica gel beads, causing a weird spike in when you take the average of the mean blue values, or an average of the blue intensity values. And so you actually see, especially right here, that there's a higher saturation, and that's not even at the base of the column. Whereas at the base of the column, you're having a lower saturation. That's important to remember for the next step of this process. All right. So our next step here is defining saturation as a ratio that goes between 0 and 1, with max saturation being a value of 1 and lowest saturation being value 0. So we take our mean values, our mean blue values, which is now a matrix consisting of all of the times, so all of the images. And we take a double max in order to take a max along the column length and a max along the row length to actually get the maximum intensity. That's what this code is doing currently. And then it takes your actual mean blue values within the entire matrix and divides them by the max blue to make them range from 0 to 1, with the max saturation being 1. Unfortunately, as we saw in those images before, this doesn't actually work very well because the maximum, there are outliers in the saturation intensities. And so you can actually get a maximum that's halfway down the column because of some discrepancies in light intensity or discrepancies in packing. And so you want to make sure that that does not happen to you and that you actually get a true saturation scheme. So what you can do is you can redefine your saturation as the mean blues again, and actually identify an averaged lowest intensity and an averaged highest intensity. And so when we're thinking about lowest intensity, we're thinking about things that have not saturated yet. And so it's ideal to think about the earliest time steps. So right here, I'm averaging over the first 3 times, or the first 3 times in the trial. Whereas in this, I'm talking about the highest points in the column, or the things farthest to the right in our cropped images. So I'm averaging over this range. It's not as noticeable with outliers in the low range or the highest part of the column, so low saturation. Where it's most noticeable is in the high range or the high saturation in the base of the column. So you want to choose the later times in your sequence because at later times you have more saturation. And you're going to choose a range that allows you to include those outliers, like include a range of those outliers in order to get like a good average maximum. And the way you know that that works is when you run the code, your saturation actually approaches 1 at the end of the column. So what I'm going to do is I'm going to run this code as it was given to you without doing this alteration and show you why there's an issue. So this was the code as given. You see that it doesn't start at 0, and it also doesn't quite reach 1. It kind of fluctuates between 0.8 and 0.9 at the base of the column, which is something you wouldn't really expect. You'd expect the lowest part of the column to be the highest saturated. And so for me, what I would do is take a range from maybe this point to this point, like a good healthy range that includes this outlier, and kind of get an average maximum so that these are actually closer to 1. And that's what we did here. I chose a healthy range from 1 to 437. Remember, your pixel length is actually 2,880. And so you're not necessarily choosing like a super large range. Just make sure it's reasonable. When I run this and then change this to SNew to match my new designation, and rerun, we'll see that we're actually starting at 0 and we're going towards or closer to 1. You'll see once it progresses further. See, we're already past 0.8, and we're already past 0.9. We're hitting 1s. Looks good. And we hit 1 in this entire region. Right. So make sure when you do this, though, that you don't have this issue that I'm having right now where the values are actually cut off. You might have to increase your range and then explain why you're going past 1, right? There are outliers. You needed to go past 1 in order to actually show a good saturation trend. There's always a good explanation for something as long as you can find it. But again, yeah, just let this run again. Make sure that you can see all the data throughout. You're getting that average 1 line there, and saturation is approaching closer to 1, like you would expect. And this range will also vary depending on what trial you're in. So this is the part of the code that you're going to have to pay attention to when you're changing your trials. All right, hopefully that was helpful. And if you have any additional questions about how to run this MATLAB code or any questions about the theory of the lab itself, definitely come and ask Josh and I for questions during office hours. We're happy to help. All right, thank you.